Name one. Name one. Number 70. All right, on 70. Up above, we're given, where the derivative is positive, where it's negative, and all that. So we're supposed to figure out if g prime of 8 is greater than 0 or less than 0. So that has a blank. That's where we're heading, to know if g prime of 8 is greater than 0 or less than 0. We start knowing that g of x equals f of x minus 10. All right, well, if I want to know something about g prime of 8, I got to get g prime of x first. So I'm going to take the derivative of both sides. Taking the derivative of g of x is a piece of cake. It's g prime of x. Now, taking the derivative of f of x minus 10 is a little different, because that's not really an f of x, is it? It's an f of u, where u equals x minus 10. So when I take the derivative of f of x minus 10, I've got to chain rule it. So remember, one of our versions of the chain rule said the derivative equals f of u times the derivative of u. That's the one I need to use. So f prime, I said f of u, didn't I? F prime of u times the derivative of u. So f prime of x minus 10 times the derivative of x minus 10. Now, fortunately for us, the derivative of x minus 10 is 1. So if you had forgotten you needed to use the chain rule, it turns out okay, doesn't it? You still end up at that line. So, we could have lucked up there and forgotten that, and it still worked out okay. So you with me to where that second check mark is? All right, now, we want to know about g prime of 8. So put an 8 in for x. So g prime of 8 will equal f prime of 8 minus 10. Well, 8 minus 10 is almost always negative 2. So g prime of 8 equals f prime of negative 2. Then we look at, and I don't think I wrote it on here, did I? Yeah, I did. So f prime of negative 2. Well, which interval tells us what the sign of f prime of negative 2 is? The first one, the second one, or the third one? Second one. So between negative 4 and 6, which includes negative 2, f prime is negative. So f prime of negative 2 is negative. Well, if g prime of 8 is equal to it, it's also negative. And if g prime of 8 is negative, it's less than 0. All right, look at these others from that same section while we're here. Because there's one of those on the quiz, so are we okay with those? Where are you at? From here to here? Yeah, the derivative of that's 1. Derivative of x is 1. Derivative of negative 10 is 0. So times 1, you don't see it anymore. All right, we good on these? Yeah. All right, what else you want to see from yesterday? Which one? All right, on 37, we're supposed to use the first derivative test to find where the function's increasing or decreasing, and we're supposed to find all the relative extrema. So we've got to do the whole thing, whole 9 yards. All right, so the extrema, the relative extrema, are going to occur at critical numbers. Critical numbers occur when the derivative equals 0 or does not exist, so we've got to find the derivative. Quotient rule. So I'll give you a minute to inspect all of that and see if you have any questions.
What I did wrong is For some reason, when I've been doing it for people lately, I've just forgot to do low, low. So,
You can't forget that.
yeah. I thought it.
We okay with the derivative? Derivatives like that seem kind of easy now. If they don't, you need to practice more. Derivatives like this ought to be easy now. Now, that doesn't mean you'll never miss one, because we can all make a mistake. But you ought to know what to do. All right, we good? Then, remember what we've been talking about. Critical numbers occur when the derivative equals 0 or does not exist. So, a fraction equals 0 when the numerator equals 0. That's how I get x plus 3 times x minus 1 equals 0. And a fraction does not exist when the denominator equals 0. So that's where I get x plus 1 quantity squared equals 0. And then we solve each of those, and we end up with 3 critical numbers. So, any questions on setting those parts equal to 0 and solving for x? Alrighty then. Now we use the first derivative test. And remember how the first derivative test works. We start from negative infinity, go to the first critical number, then the next interval goes from the first critical number to the second, then the next one's from the second to the third. And if we had more, we'd go from the third to the fourth, and then the fourth to the fifth, and finally you go from the last one to infinity. So that gives us these intervals over here on the left. And then just go one row at a time to figure these things out. So I pick a number between negative infinity and negative 3. I picked negative 10. And I find the sign of the derivative when x equals negative 10. Because remember how this works. Functions can only change direction at critical numbers. They can't change direction from up to down or down to up anywhere else. So I know for a fact that between negative infinity and negative 3, this function is either always increasing or always decreasing. It's not changing direction. So I pick one point to find which it's doing. You follow you knew it at one point. You remember the logic? All right, so turns out when I plug negative 10 back up here in the derivative, I get a positive number. I don't care what the number is. I get a positive. So that means our conclusion is that the function is increasing. Then I go to the next interval, and I pick a number between negative 3 and negative 1. I picked negative 2. I know for a fact that the function is either always increasing or always decreasing on that interval, because it can only change directions at critical numbers. So if I put negative 2 into the derivative, I get a negative derivative. That means the function is decreasing. Then you can see what I did on the last two. Picked a number, I picked 0. The derivative is negative. The function's still decreasing. Because just because the only place it can change directions is a critical number doesn't mean that it must change directions at a critical number. And it didn't. And then on the last interval from 1 to infinity, positive derivative back to increasing. Now you've got to do some thinking. All right, if a function changes from increasing to decreasing, there had to be a maximum there, didn't there? If it was going up and then switched to going down, it reached a peak value, a maximum value. And then between the next two intervals, it kept decreasing, so, nothing happened. As far as maxes or mins go anyway, nothing happened. And then between the last two intervals, it went from going down to going up, so that had to be a minimum. Don't stop there. You're supposed to find what those values are. We know where they occur. We know that the maximum occurs at negative 3. We know that the minimum occurs at 1. But go ahead and find those values. To find those values, don't use the derivative. Use what? The original function. So you go back to f. You substitute negative 3 in for x, you get negative 8. That's your relative maximum. You go back to f, you substitute 1 in for x, you get 0 to be a relative minimum. It's a little weird that the maximum's smaller than the minimum, so what must have been going on? With an asymptote, right? Okay. Questions? What's next?
Can I see what you got of the derivative of 33?
All right, we good with 33? Where am I hearing that? From the back of the computer? I unplugged the computer speakers. That'll be annoying when you listen to it. Sorry. All right, on 31. Boy, absolute value messes up everything, doesn't it? All right, so when you have an absolute value function, you're going to get either the V shape or the upside down V shape. Okay? So we need to figure out which is which. I don't know how to take the derivative with that absolute value sign. I don't. I really honestly do not know how to do that. Well, that's okay.
Can you figure out?
Nope. Because I can figure it out without having a product rule, quotient rule, an absolute value rule. I can figure it out without an absolute value rule. Okay? Because since I know what the shape's going to be, either that or that, okay, I know that where the quantity inside the absolute value equals 0 is going to either be the peak or the valley, okay? So 5. So I'm trying to figure out what's going on from negative infinity to 5, and then what's going on from 5 to infinity. Okay, well, I graphed it, and you can just make, if you want to, you can just make a little set XY table, make a little set of ordered pairs, pick a couple to the left of 5, a couple to the right of 5, and you'll be able to see whether you got that or that. Okay? Well, so the derivative was positive to the left of 5, and it's negative to the right of 5. Okay? So the derivative did change from well, let me rephrase that. The function did change directions from the left of negative 5 to the right of negative 5 because the derivative changed signs from the left of negative 5 to the right of negative 5. Okay? Now, 5 is a critical number because what's the derivative right there when x equals 5? It does not exist. I didn't work it out like I did on all the others, but do you follow the logic of it? And this is one reason why, simply trying to memorize things to imitate me eventually doesn't work all the time, because what if nobody had ever asked for this one? I never would have shown you this one, but you still would need to be able to figure it out. Okay? So everybody with me down to x equals 5 is the only critical number. Now we're back in the ball game. First derivative test, set up your intervals, pick a number, find the value of the derivative. Oh, I never worked out a formula for the derivative. That's okay. I know that to the left of 5, the derivative is positive, and to the right of 5, the derivative is negative. So my conclusion is, to the left of 5, f is increasing. To the right of 5, f is decreasing. Well, if it went from increasing to decreasing, there was a maximum. Okay? It's funny how the exceptions, the ones that aren't like all the others, even if the actual work on the paper is less complicated, they're always harder because you got to think about them more. Okay? So you're a lot less likely to make some sort of algebra mistake on number 31, but you're a lot more likely to make some sort of logic mistake on number 31. Okay? All right, what else? All right, there's 21 in all its glory.
I was thinking you had to use negative
Yeah, it's factorable. I mean, you can use the quadratic formula. It always works for a quadratic, but if it's factorable, I'd much rather factor it. Well, you know the quadratic formula. A is the coefficient of x squared, B is the coefficient of x, C is your constant. Mhm. Yeah, it gives you two. Well, it all depends, right? You could get none if you have a negative under a square root. So, right, if A is 0, you don't have a quadratic. All right, we good? All right, we'll go to 41 here in just a second. Anybody need this longer? There's 41. Well, don't you hope there's a whole lot of trig on the quiz tomorrow? You guys are so psyched out by trig. Derivative of sine is cosine. Derivative of cosine is negative sine. I'll give you a chart if you need a chart to look up values. $41 makes sense? I looked at the chart. Once I get cosine of x equals sine of x, I'll look here at the chart and say, okay, where does the cosine of x equal the sine of x? Oh, at pi over 4, because they're both radical 2 over 2. And at 5 pi over 4, because they're both negative radical 2 over 2. It is magic. The chart. Oh, I'm sure you can make it more complicated if you wanted to. But, you know. I had a request for Rolle's theorem. On Rolle's theorem, do you want a specific homework problem, or do you just want me to go over Rolle's theorem again? Just go over it? I don't know. Don't be greedy. This will make for fascinating viewing. Yeah, I'm upset that the audio doesn't work. The audio didn't work at this point last year either, so I can't even just substitute last year's videos for this year's.
So I just got there, and I guess we were talking for a long time, and that's when it sounded
Or it could have been this. We could have just all been sitting here waiting for something to happen. Ooh, something's happening.
Oh, yeah, that's right.
All right, so Rolle's theorem. The function must be continuous. It must be differentiable, which all that means is the derivative exists. And f of a equals f of b. The value of the endpoints are equal. I didn't put mean value theorem on the quiz. Not because it's not important, but just because that was about as much as I could ask you and expect you to get finished. Okay? All right, so as long as those three things happen, then there's at least one number c in that interval where the derivative equals 0. Graphically, it looks like this. All right? F is continuous and it's differentiable. F of A equals D, F of B also equals D, so F of A equals F of B. There must be at least one place where the derivative equals 0. There must be at least one place where there's a horizontal tangent line. Now, think about that. If I draw a new graph, if that's where F of A, that's F of B, okay? If my graph starts going up, it's got to come back down somewhere to get to the other end point, right? The function's continuous, no gaps. It's differentiable, no cusps. So it has to come back down somewhere. It might do this, but that's still at least one, isn't it? If it starts off down here, it's got to come back up somewhere. It might come back up, go back down, come back up. It might. But it's got to come back up at least once, doesn't it? That's all Rolle's theorem says. Okay? Yeah. Yeah. So does Rolle's theorem make sense? All right, now we did some where we actually found it. All right. So to find where the derivative equals 0, you take the derivative and set it equal to 0. And then maybe that's easy to solve and maybe it's not. Yeah. But for this particular problem, -2 wasn't in the interval. But that's a good point. We're not saying that that happens from negative infinity to infinity. We're saying this happens between A and B. Yeah, like if the interval was from -10 to 3, Rolle's theorem would not apply. Okay? All right. Does that help for Rolle's theorem? All right. Any other last-minute questions before the quiz? Where are you at? From last night? 2 nights ago. So 2 nights ago would have been... Oh, I've already got that one up. What number? Oops. There it is. Well, I tell you what, that looks a lot like your quiz question. Wow, I finally said something that got your attention. Number 60. This was from the first day of section 3.3. All right, and here's what's going on. Look, in red here is F. So, looking from negative infinity to 0, F is increasing. If F is increasing, the derivative has what sign? Positive. So I've got to draw it positive. All right, look from 0 to infinity. F's still increasing. So the sign of the derivative is still positive. But something weird happens at 0, doesn't it? Because right there, this is one of those weird things where we have a vertical tangent line. And if it's a vertical tangent line, what's the derivative there? Doesn't exist. So I got to come up with some way of drawing a function that's always positive and doesn't exist when x equals 0. Well, that does it. Always positive, doesn't exist when x equals 0. All right? All right. Anything else? I don't remember off the top of my head. My guess is all of these questions on the quiz come from one of your assignments somewhere. You know, except for the one where I ask you to list the conditions of Rolle's theorem. All righty. Okay.
Okay, so when it says, f is a rational function, so it is continuous and differentiable throughout its domain,
Uh-huh.
and then the x is not in the interval it's given, it applies.
Which number are you talking about? Oh, these usually open pretty quick. Did I just click the wrong thing? I did, didn't I? All right, 17. So the place where this function, all right, so it's rational, continuous, differentiable throughout its domain. -2 is not in that closed interval, so the theorem does still apply. Okay? If our interval had been from -3 to +3, now -2 is in that interval, and now the theorem does not apply. I would. I wouldn't want to do all that work and then have it not work. You know, just saying.